So this talk, as usual, it's about making your boat sail fast. And that's what we're doing. And I don't care how many people you hear talking about what wins, how to win races. The way to win races is to be fast. The major thing is to be fast. And people go, oh, it's about the fitness, it's about this, it's about that. But it's all about being fast. If you're quick, you're always hanging in there. And if you're off the pace a little bit, you spend all day getting gassed and pushed all over the course, and you get nowhere. So that's what we're talking about. And what I've done here on that first, have you all got that first one up that I've got up? Do they change when I change? Yes.
Yep. So we're just watching your screen, Fletch.
Yeah. So what I've tried to do here, and I did this quite a few years ago, is to try and pigeonhole the things that change the boat's performance. And the big saying is, fast sailing is about controlling power accurately, because it's different to the normal things we do. When you drive a car, you want some more power, you put your foot down. And these days, if you need a bit more, it changes gears and it does it automatically. So, but when you get on a sailing boat, you set the sails up, but then the power is controlled by somebody up in the sky. I've never met him, but I know he's got a bad sense of humour, because as soon as you get the boat set up and you're flying, you think, oh, this is fantastic. All of a sudden, he changes the wind strength. And you've got to change the power by changing the shape of the sails and trim and all that stuff, because what you're trying to do is keep the boat accurately at an angle of heel. And that's the big pointer as to whether you do it accurate, controlling the power accurately or not, is how steady your angle of heel is. And you're controlling that with your steering and with your trimming. So what we're saying first is power comes from two sources, because this is what we're talking about right through this lecture. It's getting the right power on the boat. So power comes from two sources, sail depth and angle of attack. So that's really how simple it is. There's two things you have to work on. So then it's saying, learn how to control both, because that is how you control. When Huey throws 5 knots more wind at you, you've got to control the power so the boat doesn't get overpowered or get knocked on its side. So they're the things we're working on. And sometimes when you ask for a description of how to make the boat go fast, there's hundreds of people talk for hours on it and don't say anything. And everybody ends up confused. So the sail depth and angle of attack are the first thing you've got to think about. And when I had the 29er squad that I'd worked with for a couple of years, every time I said in the morning, I said to them, good morning, boys. Where does the power come from? And they'd all yell out, sail depth and angle of attack. And that was the greeting. So that's how we want to start thinking about things. Hang on till I get, now I can see. So how a sail works is the key, and it's about aerodynamics. That makes the thing that makes aeroplanes fly and boats go through the water. So we're looking at getting the apparent wind, which is this arrow here, is coming towards the sail. Doesn't matter whether it's a mainsail or a jib. So, and you're getting flow on both sides. Not breaking the flow away. If you sheet a sail on too hard, you start to get turbulence back here, and the flow on the leeward side breaks down, and so all the power disappears. So it's the flow on the leeward side of the sail that creates the low pressure, and I'll show it here, there. So this is what we're looking at. The flow on the leeward side is high speed flow. So high speed flow creates low pressure. And these are the vector arrows that show you the force that has been transmitted onto the sail due to the airflow. And just before we go any further, I wanted to talk about vectors. I don't know how many people would do science in their studies at the moment. And a vector is an arrow showing a force that has direction and magnitude. So these are two forces here that are, if you say this is a post here with wheels on it, and you're pushing on it with these two forces here, and you want to find out which way the trolley's going to go, or the box, whatever you're pushing on, you draw the direction and magnitude with the two arrows using the same scale, and then you draw a parallelogram around it, and the line drawing the two corners of the parallelogram shows you the resultant of those two forces and the magnitude. So it's 5 units here, could be kilos or foot-pounds or whatever. 6 units here, and the resultant is 8 units in this direction. So if you want to use trigonometry or something, you can work this out, work all the forces out accurately. But if you do a quick parallelogram drawing like this, you can figure out what's going to happen. And then the guy that invented this thing, his name I can't remember, but I've got it written down here. Just quietly amongst yourselves for a second.
So we're working a little bit differently today. If you've got some questions as we're going along, please unmute yourself and ask the question, because I'm sure we'll all have a few questions as we go along. I just ask that we don't talk over each other.
So these, yeah, I'm okay now.
Good.
There you go. These forces are Newton's laws of motion. They're controlling the things that happen to your boat. And he's saying when forces are in equilibrium, so this force and the one across the middle are all established and they're in equilibrium, the body that they're pushing on either stays motionless or it moves at a constant speed. So the thing that's controlling or stopping this thing moving is drag. So if this was a cardboard box sitting on the ground and you put these two forces on it, it may not be enough force to overcome the drag of the box sitting on the table, and it'll stay stationary. Okay? But if the forces are big enough, if you increase them from 5 units to 10 units and this one from 6 to 12 units, all of a sudden this force will get bigger, and the box, the drag on the box will be overcome, and it'll start to move. Now, as it moves, the drag goes up until the forces get in equilibrium again, and then the box will move at a constant speed. So see what we're getting at here? It either stays stationary because the drag's too high, or it accelerates to a point where the drag becomes equal with the forces that are acting, and then it starts to go at a constant speed. And this is what sails do. You go out and the boat's sitting in the water with the sails flapping, and it's actually got drag doing that. So you've got to hold it from going backwards. Now there's no flow on the sails, so when we hop on board and we get some flow on the sails, all of a sudden you've got side force and force pushing you forward. Now, the boat then, the forces are not in equilibrium, so the boat starts to move. As soon as it moves, the drag starts to act on the boat. And this is the hull pushing through the water, the wind going across the sails, all the things that cause drag are starting to oppose the driving force. So as soon as the forces get in equilibrium again, you go at a constant speed. Now, if you think about when I used to sail dinghies, I didn't know anything about this, and I could beat anybody because I'd just hike harder and I'd burn them off, and that's how you thought races were won and lost. But when I started to sail keel boats, when I came to Sydney and started to be a sailmaker, I realised that when you race dragons, they're displacement boats, and they had a maximum speed for every wind strength. So you could get a boat that's a boat length in front of you, and he'd be there for 2 laps because he wasn't making any mistakes and neither were you. So once you get the forces acting on the boat accurately, the speed stays constant. So there's a diagram over here that just shows that you can change the forces to any direction you want. As long as you use parallelogram, the square's a parallelogram, you can work out what's happening with the forces. So, seeing we've done that, now when we look at this airflow on the sail here, you can see all these arrows here are vector forces, and the ones in the front of the sail are pushing forward, less forward, sideways. So there's dead sideways, the force is here. So there's no drive forward there. And then as the forces get smaller, there's less pressure difference. So the pressure difference on the sail reduces to there where it's nothing. And the molecules of air that get on the front here, the ones that are going slower here, and the ones going fast here, each molecule of air that gets on the front here has to get the back at the same time. Otherwise, the universe blows up. So that the air, when it comes, the bigger the speed difference from the leeward side to the windward side, the higher the pressure. So the higher the pressure, the more likely the sail is to stall or get turbulence. So as you get down here and the pressure's equal and goes off the back, all the work has been done as the air moves around here. So, and the leech of your sail flutters, you've probably all seen that. And that's because there's no pressure difference here. So the sail doesn't quite know what to do. And in the old days where sails were hooked up on the leech and things like that, they didn't flutter much. But when we got really good materials and good cloths that didn't stretch, backs of the sails were really, really straight, and the sails started to flutter. And you had to pull the leech line on with genoas and things like that, head saws, to stop them fluttering. And Norse actually drew the drawings on their promotion sail diagrams with a little return on the edge of the leech, because everybody thought that was disastrous to have that. But when the flows come right across the sail to here, by the time it gets down at the back here, it's all done its work with the pressure differences here. So it's not a big deal. So when you put a foil like this in a wind tunnel, and you can control the wind speed and the angle of attack very, very accurately. They put them in a wind tunnel like this diagram here, and there are dials on the floating platform that measure drag, and a dial out here that measures lift. So this lift force here will show up on a dial that it's so many kilos or whatever it is, grams, and here it'll show drag. So and in the wind tunnel, you can rotate this sail around and increase the angle of attack by doing this with it. I haven't got one with it drawn there. So as you increase the angle of attack, the lift goes up. And it goes up and up and up, and the drag stays pretty much the same. And that's what we're doing when we're sailing our boats. We change angle of attack by steering. When you bear away a little bit, you'll all know this, you feel the power go up. And as you point higher, the power goes down. And that's because you're changing the angle of attack by steering on the whole rig. Now, this is just a lift and drag diagram. So what we're going to do now is change that into something. Yes, this, no, we're not. Hang on, I'll get back here. Can't get what I want. I don't know where this drawing is. Anyway, we'll talk around it. So just going back now to where we were, was the power comes from sail depth and angle of attack. So we'll look at sail depth. How do we define it and how do we control it? And the depth of a sail is measured as a percentage of the chord length. So that might be most sails are like dinghy sails are 12 to 13, 14% deep. So so that's how it's measured there. And here, the position of the drive, whether the drive's forward or whether it's aft, and that has a big bearing on the efficiency of the sail. So it's measured as a percentage of the chord length again, and measured as a percentage back from the leading edge. Okay, so this is the mast up here. So then the next thing we've got is mainsail depth. Hang on. Now, how do we control the mainsail depth? So this is the next thing, is the sail is designed by the sailmaker and it has depth built into the sail, like seam shaping, and that depth you can't change because it's built in there. But the other thing that changes mast bend is the depth is mast bend. So as the sail, you can see over here, as the mast bends, it pulls the depth out of the sail from here out to here. The sail gets flatter as it bends. So the other thing that controls mainsail depth is boom and outhaul the outhaul adjustment along the boom, and Cunningham, but especially on dinghies Cunningham, because it helps bend the mast. So that there's only 1, 2, 3, 4. You don't have to worry about this one because that's in the sail that you buy from the sailmaker. And in laser sails, all your laser sails are the same. So you just don't have to worry about that at all. All you have to worry about is mast bend, boom outhaul, and Cunningham. 3 things that control depth. And that would be the biggest problem I see watching boats sailing around Sydney Harbour, that their sails are the wrong depth. And when you see it's blowing a little bit, boat's lying on its side, massive weather helm on the boat that's all drag, and the boats can't control the angle of heel, and it just every time you get a gust, it leans over and sticks the rail in the water. More drag. So that's one of the biggest problems, and it's so simple. You know, it's the only thing that controls the sail depth is mast bend, boom out hole, and Cunningham, and they've got them all wrong. So that's why we need to look at these things. Now the jib is the same. It's the design. We're not using jibs. We might as well talk about them because sooner or later you will use one. And that's the design again, same shape. Forestay sag, as the forestay sags, and so I've got a dotted line here, the sail gets deeper. So the forestay sag needs to be controlled as the wind goes up. And normally, you know, in most boats, you've got rig tension, which helps hold the forestay up. And yachts, you have backstays and runners and all sorts of things to try and hold the forestay up. But generally, we're fighting a losing battle. And if we can control, just keep the forestay sag where it needs to be, then we can get through a lot of wind up and down, you know, just using the forestay control. So sheeting fore and aft with a jib car position, you don't have to do that on your boat. So, and the luff tension is the same. So on the jib, it's forestay sag, sheeting fore and aft, and luff tension. So there are not that many things to think about. And this diagram shows what angle of attack is. It's the chord length, it's the chord angle of the sail projected out here, and the apparent wind coming in here. And the difference between those two is the angle of attack that the sail's working at. Apparent wind at an angle to the chord of the sail. Now you can see that this is the apparent wind angle, which has nothing to do with angle of attack, but it's the thing that we see acting on the sail. We see the sail luffing and stuff like that, and that's caused by the apparent wind. We're steering the boat too high and the sail's blowing inside out, or we're sailing it too low and the sail stalls. So when you sail too low, sail stalls and the power goes down and the drag goes up. So,
Fletch, I'm just going to interrupt you there, and I'll
yes.
remind everyone that they can unmute themselves and ask a question as we're going along. We've got some young sailors with us and they might not have heard the term apparent wind before. Do you want to explain that?
Yeah, the apparent wind is the wind that you feel, and because your boat's going forward at say 5 knots, the boat speed induces apparent wind. So if you're sitting in your car and there's no wind and you put your hand out the window and you're going 5 knots, you feel 5 knots of wind. And what the boat's feeling is the apparent wind is added to the true wind, and that's the wind that the apparent wind, or the apparent wind speed that the sail sees. And when you get into bigger, faster boats like the 100-footers that go to Hobart, they're sailing upwind doing 12 or 14 knots. So that adds to the boat, to the apparent wind speed. So when they're sailing in upwind at 14 knots in 15 knots of wind, like they're sailing in over 30 knots of wind speed, which is a lot of wind. So as you guys get to start hiking in your laser, because your boat's going faster, you're getting more wind across the sail due to your boat speed. So that's what you feel is apparent wind. So it's that simple. It's just the boat speed added to the wind speed. Okay. Have we got any other questions coming in?
So feel free to unmute and ask a question if you've got one.
I've been talking about this stuff for years, and sometimes you have to hear it half a dozen times before you get a handle on it. So don't worry about asking a question. We're all in this together. Some people think, oh, I won't ask that question because it makes me look like a bit of a dill, but it's not. We're all a bit dillish when we first hear this stuff. So we've all got a handle on, should have a handle on sail depth, draft position, fore and aft, how to control the sail depth, mainsail, 4 things, the same shape that's designed in, so we don't have to worry about that. Mast, bend, boom, outhaul, Cunningham. And that's because you guys, the laser sails only have to worry about one sail. That pretty much happens automatically in an unstayed rig. But then the boom outhaul, the Cunningham, and that sort of stuff, they're the 2 critical things you've got to worry about in a laser radial. It's the boom outhaul and the Cunningham. The mast bend is all to do with the mast stiffness, the tubes that are stuck in the deck, and how much they bend. And the sail twist, which we'll talk about in a minute, that's also automatically controlled in an unstayed rig. So one of the big depth controls on the laser radial is how hard you pull the sheet on, because that's what's bending the mast. Does everybody get that? Some of these other sketches we've got here is this one on twist, so that a mainsail, when you're using it in stronger winds, it twists open as you go up the sail. That's sort of the middle thing, and you see the chord here is way further open than the bottom of the sail, and then it's more open up here. So as you go up the sail, the sail's getting less and less powerful because you've got twist in the sail. So the sheet pressure is also controlling. So if you had a sail looking like this one and you sheet it on, all these angles here would come in like this closer to the boom, and the top of the sail would power up, and you'd feel a lot more power acting on the side of the boat. So you see on this sketch here, we've got the apparent wind coming on, working on this sail, and when we ease the boom off centerline, which a radial has it out here all the time, but when they put them out over the side of the boat, it depowers because the angle of attack goes down. And you'll see here that, for future reference, this is say a 420 or a 470 or any boat with a jib on it. The mainsail sheet much closer to the centre line, because the flow off the jib going back around the mainsail depowers the bottom of the mainsail, and because the pressure difference is a lot less, you can sheet it much closer to the centre line without any stalling effect. So with a laser, because there's no jib there, it's always powered up, the flow on the sail. So you carry all, cat rigged boats with one mainsail or anything, moss, all these things, they all sheet a lot wider, but they still point at the same angle as the boat does with a jib on it. So then, the thing I've been talking to about and was pointing out in the video we looked at the other day was how people, the girls were easing the boom out to here and back in again and working this angle here to control the power in the mainsail. We all...
Fletcher, we've got a question here.
Yeah.
It says, I'm a dad still helping my sailor set her rig up. How best can I make practical notes about matching conditions and rig settings to get a good consistent setup?
Is it a radial?
No, I think this is coming into this is just starting out in an Optimist.
Yeah, an Optimist's exactly the same. They just have different things that set the sail up, and one's the angle that the sprit goes up at. I'm just trying to visualise. I've played with them enough. But if you pull the sprit up, the sail gets deeper. And if you let it hang back, it's like getting more mast bend, and you start to get creases across the sail. So that's very critical to get that. And I can't remember now whether there's I think it's just one halyard, isn't it, on the mainsail?
I think it's a...
it's like a lug wrist.
There's one control rope that you could actually have marks in it and stagger your marks.
That's got to be calibrated accurately, and you need to get to look at the sail too. I've just got some sketches back here somewhere. See these sketches here. If you've got the creases down your sail like this, and this could be your gaff up here and the mainmast down here. If the creases are all coming away from where the gaff is here, they're coming away like this or like this. Here's the one here. It's behind me. It's on there. But all the creases are here are coming from the middle of the mast, and that's what your Optimist sail will look like if the gaff's hanging back too far. And if it's just right, you'll see little creases all the way down like this. And if it's got creases like this, they're overbend creases where the mast is bending too much. So get to look at the sail and read where the bend is, if the bend's correct or not. And in a oppie, you can adjust it by using the halyard to pull the sprit up and down. And the foot out haul is the same. If you ease it in, it'll be very deep, and you can have them too deep, so it's good to get somebody it's good to look at it. If I'm down there one day, so can you have a quick look at this? And then get some calibrations on your out haul line or on the boom itself so that you can see how hard it's pulled out. And the next thing is the sheet pressure on a, where is it? Looking down shot. Yeah, see the angle we're looking at here on to the centre line. This is a boat with a jib, like a 420 or 470. This is a laser radial that's only got one sail. So as soon as you go to the opties, their boom points right, goes right over the corner of the boat. It's the right spot. And so what I do when I'm coaching them, and little boats like this with juniors, I get them out sailing, and I get the sail so it looks really good, and the boom's pointing over the edge here, and the boat's sailing along nicely, and then I say, don't move the sail, and I lean into the boat and put a black texture colour mark on the main sheet where it comes through the snatch block. So that when you say, right, we're going upwind, they pull it straight to that mark, and then they're not reaching around because the sail's not pulled on hard enough. And then you teach them to ease it a bit in the gust and pull it on a bit in the light spots. but you use the mark, and they can see then how much they're pulling it on and off, and they learn very quickly where it should be. Does that help?
Mike, it's Sean here. Thanks very much for that. That's a good tip on the texter.
Yeah. And that sort of works. You've got to do things that get people up quickly.
And that works on any boat.
Yeah. It's just calibrating the adjustments, really. And the lasers are the same. Any other questions?
Fletch, we've been going for a bit over half an hour. I'm wondering if you should go to the slide that talks about bang sheeting and sheet sheeting, and then that might be a good one to finish off on.
Righto. Yeah, this one here. It's a good question, because the twist of a sail is what changes the power. If you have your sail set up like this with a lot of twist in it, you're depowering the top of the sail and using the bottom for power. So that's pretty good when it's windy and you're hiking to try and keep the boat up. And when it's lighter, you want the sail set up like this, so the sail's at high angles of attack all the way up and down. Now, a radial can't change that much, because when you sheet on, you're bending the mast. And the load you get in the leech here, going from the top of the mast down to the end of the boom, it's got to be correct. If it's too tight, you won't be able to steer the boat. So the thing that stops you getting it too tight is that the boom comes block to block. And a fin is like that. And a lot of the unstayed masts are like that. So that when you pull the sheet on, the mast's the right stiffness, so it automatically lets the sail twist open when it gets windy. And by pulling lots of Cunningham eye on, that tends to encourage the mast to bend and keeps the sail looking more like this than like this. So, so that's the sheet tension. The vang sheeting is when the vang controls the whole twist. So, and that's what, when we were looking at those videos the other day, the girl sailing the medal race in the radials, they were full sheeting, because when they used to sheet, the boom went out horizontally. It just went out like this, straight out like this, parallel with the water. Sorry. There. It goes straight out like that and depowers. It doesn't change the twist. Whereas if you're sheeting and you ease a little bit, the twist comes in straight away, but the boom stays on the centre line. So if you're sailing a dinghy, you need to get the boom off centre as soon as the power goes up. So you do sheeting, vang and sheeting. This is what you do. So you've got to the stage where you've eased the sheet a little bit and the boom's still in here. But now you want the boom to go out, but the twist to stay the same. So then you pull the sheet on hard enough to control the twist. So when you ease the sheet, the twist doesn't change. So now so when you're setting the vang up, you're sheeting, and when you ease, it automatically goes to the twist for the up pressure. So you've got to have the two things set up properly. When you're sheeting and you sheet it through the vang, and you do this when the pressure's going up and down, sheet through the vang, and then when you get a hard gust, you ease, and the twist goes automatically to the twist to depower in the up pressure. So that's what happens. And the bigger the boats you get, the less you can control the sheet. So you end up, sailing the boat with sheet pressure all the time. The other thing that happens too is I don't know if I've got something here that here. If you've got a vang that's going across here, and you're sheeting fully, the main sheet's not doing anything, it means that the berm's springy. The berm can spring up and down here, and that allows the berm to twist as you get a gust, and you're sheeting in here and you ease, it goes out here, the twist goes out, and that's where the vang stops it, and then your berm goes out off centre. So if you want a little more power when you ease the berm, you have just tighten your vang a bit, and it changes the twist. But when you need full power, you sheet through the vang, and the twist comes out completely. Okay, does that give you a bit of a clue on what we're talking about? And here's the main saw that is showing twist. I'll show you this on a diagram here. This is a photograph of an etchel sail, and what we've done, you take the photograph from down here, halfway along the berm, up on the windward side of the sail, and the stripes that are on the sail at half height, three-quarter height and quarter height, you can draw the lines. Once you've taken the photograph, you draw the lines across the sail like this and measure the depth. And so when you look at the photograph like this, it shows the twist and the depth as the sail depth up and down the sail. And this has got I haven't got it here, but there's a scale on there, and it mentions the twist at 1, 2 and 3, and it reads the angle of twist and all this stuff, and it's done in the computer. So once you get this photograph in the computer, if you've got a program, it just reads it and comes up with all these measurements. So that's what we're looking at when we're talking about twist. It's something that that you see on a dinghy, and we used to photograph them, and we used to photograph the fin sails to get the depths of the sails right. And I mentioned before, when you sheet a sail on, the load that goes down the leach is really critical, because if it's too hard, when a gust hits it, it doesn't have any resilience, it doesn't move. You want the leach to just move a little bit like this automatically without changing anything. And it's really critical in an unstayed rig. So the Finns realised that this load here was really critical. So they have a piece of wire that's the same length as the leach of the sail, and they have a spring balance put in it. So they hook it onto the berm, and they sheet the sail to the deck, and the scale on a fin, it mostly reads about 5.5 kilos. And if you're a big guy and you've got plenty of rod moment here, then you might be able to carry 6 kilos on the scale. And if you're a bit light, you might only get 5.25 kilos. But this load that's up here is critical. And with a laser radial sail, because your berm hits the deck here, it's automatically controlled. But when I was coaching them for the Olympics, I actually had one of these wires with a gauge in it and hooked to the berm, so we could pull the berm down block to block and read the gauge. And in those days, they were aluminium extrusions, and some were softer than the other. And they just had a massive problem with the performance of the boat, because if you've got a soft top section, the sail would go much flatter in the top than somebody who had a stiff one. So if you were sailing in moderate conditions, they'd just burn you off. Now they've got carbon top sections. I think that's happened to try and control that. How are we going? We got any
All
other
right.
questions?
I think, has anyone got any last questions? We've been going for a while. I think it's time for us all to stretch our legs. There's quite a lot of information there to digest, and as Fletch said, you hear it for one time, then you hear it again, and it does take a little while to digest.
And when I'm coaching it, I'll mention these things. Like you got too much load in your main sheet leach, and that means that you've got to get more Cunningham on or something like that. So it's important to eventually, have a good grasp of what we're talking about, and you don't have to think about it when you're sailing. You just automatically do it, and if the boat feels bad, you just glance up and you say, where does the power come from? Sail depth and angle of attack. What's the depth like? It's too deep. How do we flatten it? We bend the mast more. So you just get to the answer with your speed problems. You get there really quickly because you don't get muddled around with the Cunningham and the outhole and all these things. You just think quickly into what controls depth, and you come to the answer straight away. Any other questions?
I think it might be easier for a lot of our guys to learn while doing as well, which would be great to have your feedback on the water, Mike.
Yes, and that's why I do the lectures, because when I mention something out in the water, you'll have a good handle on what we're talking about.
Can visualize it for sure. And I know a lot of laser sails, they mark where they want their ropes to be for different wind strengths and that kind of thing. But is it better to start off, if you're starting off as a laser sail, is it better to start off by just looking at the sail and then adjusting to the shape of the sail? Or is having markings on ropes good too?
The best thing with a laser is the fact that your blocks are very close together, and you've got to get good at just glancing back and knowing that they're like a hand width apart. And,
sure.
And in this wind strength, when I'm just hiking and I'm looking for a bit of power, I want them about 2 hand widths apart. So when you glance back there, that's what they should look like. It's easy to judge that distance because it's a small distance.
Sure.
And then as you feel the pressure going up, you need to flatten. So you sheet a bit harder, and you might go down to 1 hand width. And then when you get to the stage you're fully hiking and you need to depower, then you use the Cunningham and you get block to block. And then the next thing is I need to get rid of some more power. Then you're fully bang sheeted. So when you use the sheet, it just goes out. So there's a really clear step for laser radials. And that's what it is. And the full rig's the same. So everybody understanding that one?
Sounds good to me. Did you guys have any questions, guys? Any questions from our squads?
Everybody should have seen that on the videos of the top girls in the world. Fine trimming all the time.
All right, I think that we might call it a note there. I was just, we had a question about whether these webinars are available to view afterwards. And yes, they're available via the club's YouTube channel. And I think we can share these notes too, can't we, Fletch? The diagrams might help people. So I'll send them out to everybody, and that might actually help us with some questions for next week too.
Half the coaches in the world have got them, so a few more won't do any harm.
Right. All right. Well, thanks everybody for joining us tonight, and we look forward to seeing you again next week. Angus, anything else to say?
No, that's it. Thanks, guys. Thank you very much, Mike, and thanks, Karen.
With a bit of luck, we might be able to do the second half of this then.
Yeah, that'd be great.
And maybe we can get some questions to ask the slides as well.
Yeah, you need to have time to have a think about it, and then I'll go through them again quickly, and then we'll do the last some other stuff.
Okay, great.
Good.
All right.
All right.
Thanks, Fletch.
See you
Thank you,
later.
everyone, for joining us. Bye.
Thanks, guys. See you next week. Bye.
Bye. Bye.